A single point of light outshines an entire galaxy. This is a quasar, the heart of an active galactic nucleus, and it is the most powerful engine in the known universe. These are not calm stars but monstrous, chaotic beacons powered by supermassive black holes, and their behavior shatters everything we thought we knew about physics. By the end of this journey, you will understand 25 of their most bizarre and mind-bending phenomena. We will see jets that appear to break the universal speed limit and engines that flicker on and off like cosmic light switches. How can an object that anchors a galaxy also hold the key to its own destruction? But this illusion of impossible speed is our first glimpse into their true nature. We call this superluminal motion, and it is the first of our 25 bizarre phenomena. For decades, astronomers pointed their radio telescopes at these brilliant cores and saw something that should not exist. They watched blobs of plasma shot out in jets from the active nucleus, apparently racing across the sky at many times the speed of light. The math was clear, the measurements were repeated, and it seemed to violate the most fundamental law of physics. Nothing with mass can travel faster than light. The universe itself forbids it. So what were they seeing? The answer is a breathtaking trick of perspective and physics, a relativistic illusion. Imagine a speedboat on a lake racing almost directly toward you. If it were to blast water jets to the sides as it came, the wake from those jets would appear to spread outward faster than the boat itself is actually moving. Now replace the lake with the fabric of space, the boat with a blob of plasma traveling at 99.9% the speed of light, and point it almost but not quite directly at Earth. The material is chasing its own light, because it is moving so incredibly fast and so nearly along our line of sight. The light it emits later has a much shorter distance to travel to reach us than the light it emitted earlier. Our telescopes see the later emission arrive not long after the earlier one, making the object appear to have crossed a vast distance in an impossibly short time. It is a cosmic jet ski creating a wake that seems to outpace reality itself. This phenomenon, called relativistic beaming, does not break Einstein's rules. It confirms them in the most extreme theater imaginable. The initial shock it gave astronomers has faded, replaced by awe. We are not seeing a law broken. We are seeing a law written in fire. That illusion of speed is only possible because of the raw, unfiltered violence at the very center. To understand the quasar, you must first understand the engine that drives it. This brings us to the second bizarre phenomenon, the ultimate power source, the physics of the accretion disk. Picture, if you will, a whirlpool on a cosmic scale. Not of water, but of stars, gas, and dust, all spiraling inward toward an abyss. This is not a neat, orderly orbit. It is a chaotic, screaming maelstrom. As this immense river of matter flows inward, it does not go quietly. Particles rub against each other with unimaginable force. This friction, on a scale we can barely comprehend, heats the material not to thousands but to millions of degrees. The disk becomes a furnace so intense it does not glow with visible light. It screams in X-rays and gamma rays. It is a cosmic particle accelerator, smashing atoms together and tearing them apart before they ever reach the point of no return. That point has a name, the innermost stable circular orbit. Think of it as the final ledge above a waterfall. Up to that ledge, matter can, in theory, still find a path that keeps it circling. But once a particle crosses that invisible boundary, the grip of the black hole's gravity becomes absolute. There is no more circling, no more stable orbit. It is a one-way trip into oblivion, lost from our universe forever. This process of feeding the abyss is staggeringly efficient. In our Sun, nuclear fusion converts only about 0.7% of mass into energy. Here, in the fury of the accretion disk, the conversion is up to 10 times more effective. Mass does not just burn, it is annihilated with a ferocity that makes the heart of a star seem gentle. This is the furnace that lights the beacon, the reason a single point can outshine a galaxy. And from this raging disk, the universe's most powerful jets are born. From that raging disk of annihilated matter, the universe does not just create light, it forges weapons. These are the relativistic jets, colossal beams of charged particles and radiation that blast outward from the poles of the black hole's accretion disk. They are not gentle streams but focused cannons, punching through the surrounding galaxy and extending for thousands, even millions, of light years into the intergalactic void. To grasp their scale, picture our entire Milky Way, a spiral 100,000 light years across. Now imagine a beam of pure energy shooting straight out from its center, piercing through the galaxy's heart and stretching 10 times its length into the empty darkness beyond. That is the power of a quasar's jet, but here lies a profound mystery, the third of our bizarre phenomena. How do these jets stay so perfectly focused over such unimaginable distances? A garden hose loses pressure, a laser beam spreads out, yet these jets remain tightly collimated like cosmic searchlights for distances that dwarf galaxies. The leading theory points to a force invisible to our eyes but supremely powerful: magnetic fields. As the supermassive black hole spins, it drags the fabric of space-time around with it, an effect called frame dragging. This spin, combined with the violently rotating accretion disk, is thought to wind up magnetic field lines like cosmic springs. These fields become twisted tubes of immense energy, channeling and squeezing the erupting plasma into those narrow, ultra-fast beams. It is a natural magnetic nozzle focusing the universe's most powerful eruption. Not all jets are created equal, however. Their appearance depends entirely on our viewing angle. When one of these deadly beams is pointed almost directly at Earth, we see a blazar, a source of such violent and unpredictable brightness it can outshine every other object in its region of the sky. These are the jets in their most raw and terrifying form, a continuous barrage aimed right at us. From other angles, we see the jets from the side, witnessing their majestic, extended structure as they plow through intergalactic gas. Some active nuclei produce sporadic, gurgling jets, while others seem to fire in steady, relentless streams for eons. Each variation is a clue, a different perspective on the same monstrous engine. These jets are more than just spectacular light shows. They are the black hole's way of regulating its own growth, a violent release valve that heats the surrounding galaxy and can shut down star formation forever. They are the smoking gun, the visible proof of the chaos within, and sometimes that chaos is so great it leaves behind a ghost. The ghost of a jet can linger for millions of years. But what if the monster itself could change its face simply by how we look at it? This brings us to our fourth bizarre phenomenon, the cosmic shape-shifter, known as the active galactic nucleus unification model. For decades, astronomers catalogued different beasts in the celestial zoo. There were quasars, the brilliant beacons; blazars, the violently flickering points; and Seyfert galaxies, active cores nestled within visible spiral arms. Each had its own signature, its own personality. The natural assumption was that these were different types of objects powered by different kinds of engines. But a strange suspicion began to grow. What if they were all the same monster, just seen from different angles? The key to this cosmic illusion is a simple yet profound structure, the torus. Imagine a gargantuan, thick donut of gas and dust, light years across, encircling the supermassive black hole and its blazing accretion disk. This is not a solid object, but a swirling, turbulent fog bank on an unimaginable scale. Now picture yourself floating in space around this system. Your view of the central inferno depends entirely on where you stand. If you look down from above the donut, you have a clear, unobstructed view straight into the engine room. You see the brilliant accretion disk and the base of the jets. This, from our distant vantage point, is what we classify as a quasar or a blazar, depending on if the jet is pointed at us. But if your line of sight is through the edge of the donut, the view changes dramatically. The thick dust and gas block the most intense optical and ultraviolet light from the disk. You might still see some activity, the glow of heated gas further out, but the brilliant core is hidden. This is what we see as a Seyfert galaxy, an active heart shrouded in its own fuel. From the side, looking directly through the thickest part of the torus, the central engine might be completely invisible at certain wavelengths, shrouded in cosmic soot. This single model, a supermassive black hole, an accretion disk, jets, and obscuring torus, elegantly unifies a menagerie of objects into one. It tells us that classification in astronomy is often a matter of perspective. A quasar is not a different creature from a Seyfert galaxy. It is just a Seyfert galaxy we are looking at from the top down. Yet, as with all things in this realm, mysteries remain. How does such a torus stay stable? What feeds it and what determines its thickness? Some observations suggest it might be more of a chaotic, clumpy cloud than a neat ring. The unification model is a powerful framework, but the devil and the discovery is in the dusty details. It reveals that the universe often shows us only one face of a multidimensional truth. But a stable shape is the last thing you would expect from these engines. They are not steady lighthouses, but frantic, flickering strobe lights. The light from a quasar does not shine with a constant glow. It dances, it pulses, it brightens and fades over timescales that range from mere hours to decades. This erratic heartbeat is our fifth bizarre phenomenon, and it holds a crucial secret about the true size of the monster's core. Think of it this way: information cannot travel faster than light. If the entire face of a giant object were to brighten at once, the signal to brighten would have to travel from one side to the other, limited by the speed of light. So, if we see a quasar's brightness double in just a few hours, that tells us the region responsible for that change cannot be larger than a few light hours across. A light hour is the distance light travels in 1 hour, about 1100 million kilometers. That is still an immense space, but compared to a galaxy, it is vanishingly small. The most violent fluctuations confine the powerhouse to a region smaller than our own solar system. From a volume no larger than the orbit of Pluto, a quasar can outshine hundreds of billions of stars. This is the ultimate cosmic concentration of power, but what causes the flickering? The leading suspect is the accretion disk itself. This maelstrom of superheated gas is not a smooth, serene whirlpool. It is subject to violent instabilities. Magnetic fields can snap and reconnect, releasing enormous bursts of energy like solar flares on a catastrophic scale. Dense clumps of matter might spiral in suddenly, causing a temporary surge in brightness as they are torn apart. Another possibility involves shadow play. Thick clouds of cooler gas within the torus or the broadline region could drift in front of our view of the brilliant core, momentarily dimming its light in specific wavelengths before moving on. It is as if smoke from the engine's own exhaust occasionally blows across its headlights. Astronomers study these light curves, the graphs of brightness over time, like doctors reading an EKG. Each dip and spike is a clue. Rapid, small flickers might come from the innermost, hottest part of the disk. Slower, grander changes over years could be tied to larger shifts in the fuel supply or the jet's activity. This variability is not a bug in the system. It is a fundamental feature, the turbulent breathing of a billion-sun engine crammed into a space we can barely comprehend. And sometimes that breathing stops altogether. Sometimes the flickering stops because the monster is not just breathing in, it is screaming out. The light from a quasar is not merely a beacon, it is a cosmic hurricane. This brings us to our sixth bizarre phenomenon, the cosmic bellows known as broad absorption line quasars. To understand them, we must learn to read the hidden messages written in their light. When astronomers break a quasar's light into a spectrum, a rainbow of colors crossed by dark lines, they see a familiar pattern. bright emission lines created as gas glows fiercely near the black hole. But in about 10% of quasars, something strange is superimposed on that glow. Deep, broad, dark absorption lines are carved into the spectrum. These are not just shadows, they are signatures of a titanic exhalation. The gas creating these lines is not sitting still, it is moving and moving fast. The critical clue is where these dark lines appear. They are not centered on their expected color, they are shifted sharply toward the blue end of the spectrum. In the universe, a blue shift means one thing: the object is hurtling toward us. Here, the gas is streaming directly into our line of sight at velocities that beggar belief, thousands, even tens of thousands of kilometers per second. This is not a gentle breeze, it is a supersonic gale of matter being blasted outward from the very heart of the quasar. What force could possibly propel such a wind? The answer lies in the sheer intensity of the light itself. Picture standing too close to a colossal spotlight. You would feel the pressure of the photons, the particles of light pushing against you. Now amplify that by a factor of billions. The radiation pouring from the accretion disk creates an immense outward pressure, a physical force that acts on the surrounding gas and dust. In the dense, turbulent clouds near the black hole, this radiation pressure overcomes the mighty pull of gravity itself. It grabs hold of the material and flings it outward, accelerating it to a significant fraction of the speed of light. These are not jets, which are narrow beams. These are wide-angle outflows, a vast spherical or conical shell of material being purged from the galactic core. But why does this matter? This is where the quasar transforms from a destructive force into a cosmic regulator. This process is called feedback. As these furious winds blast through the host galaxy, they do something profound. They sweep up the raw material for making new stars, the cold molecular gas, and they heat it, disperse it, or blow it entirely out of the galaxy. Imagine a giant bellows pointed at a bed of glowing embers. The bellows does not feed the fire, it scatters the embers and cools them, preventing a new blaze. That is what these quasar winds do. They can quench star formation, effectively putting the galaxy's stellar nursery on hold. In this way, the supermassive black hole, by the very act of its own violent feeding, may set a limit on the growth of the galaxy that surrounds it. It is a self-regulating cycle of cosmic proportions. The monster, in its rage, shapes its own world. Yet for all their power, these winds are not the final word. The quasar has another, even more direct way of making its presence felt, a way that reaches across the deepest voids. The most extreme form of this flickering is not a change in brightness, but a complete transformation of identity. This is our seventh bizarre phenomenon, the ghost in the machine known as the changing look quasar. Picture a lighthouse that has shone brilliantly for decades, a steady guide in the cosmic dark. Then, within just 2 or 3 years, its light simply winks out. The beacon is gone, or in the reverse scenario, a seemingly ordinary galaxy suddenly ignites, becoming a brilliant quasar in a geological instant. These are not gradual shifts over millions of years. They are metamorphoses that happen within a human lifetime, and they pose a profound challenge to everything we thought we knew about fueling these giants. The central engine of a quasar, a supermassive black hole millions of times the mass of our Sun, is an object of immense inertia. It should be the very definition of stability. How could something so colossal switch on or off like a cosmic light bulb? Astronomers have witnessed both scenarios. In one famous case, a quasar that had been brightly shining for over a decade dimmed by a factor of 10 in less than 3 years, its broad emission lines vanishing as if they had never existed. It went from a brilliant monster to a quiet galactic core, essentially overnight. The leading explanation points to the fuel supply. Think of the accretion disk not as a steady river, but as a chaotic, clumpy downpour. A sudden, massive influx of gas, perhaps from a shredded star or a destabilized gas cloud falling inward, could flood the engine, causing it to flare brilliantly into a quasar state. Once that dense clump is consumed, the accretion rate could plummet just as rapidly, starving the disk and causing the brilliance to fade. It is like a cosmic dam breaking, unleashing a torrent, and then just as quickly sealing shut. Another compelling theory involves the obscuring torus, that giant donut of dust. What if a particularly dense knot within that torus drifted directly across our line of sight? From our perspective, the brilliant central engine would be abruptly cloaked, turning a quasar into what looks like an ordinary galaxy. A few years later, as the cloud moves on, the quasar would reappear. This would be an illusion, a shadow play on the grandest scale, but it would mean the monster was always there, simply hidden from our view. The terrifying truth is that both mechanisms might be at work in different objects. These changing-look quasars force us to confront the sheer violence and instability of the feeding process. They reveal that the state of quasar may not be a permanent condition for a galaxy, but a phase it goes through, flickering in and out of brilliance as it feasts. It suggests our night sky is not a static picture, but a dynamic show where titans can awaken or fall asleep before our very eyes. And this variability hints at an even deeper instability, one that might explain why these engines are so hard to ignite in the modern universe. The quasar's flickering light is a message, but sometimes that message passes through a cosmic funhouse mirror before it reaches us. This brings us to our eighth bizarre phenomenon, the gravitational maze known as quasar microlensing. To understand this, we must first grasp the power of gravity to bend light itself, a prediction of Einstein's general relativity. A massive object like a galaxy can warp the space around it so profoundly that light from a more distant object like a quasar is forced to travel along curved paths as it passes by. This can split the quasar's single image into multiple copies, creating beautiful patterns like the famous Einstein cross, where one quasar appears as 4 points of light arranged around a foreground galaxy. But there is a deeper, more chaotic layer to this effect. Within that foreground galaxy are not just a few stars, but billions of individual suns. Each one of these stars also bends space, acting as a tiny, moving gravitational lens. This is microlensing. As the stars in the intervening galaxy drift through space, their minute gravitational fields pass in front of the distant quasar's light path. Each star acts like a magnifying glass, but one that is imperfect, moving and distorting. When one of these stellar lenses passes almost directly in front of a specific part of the quasar, a remarkable thing happens. That tiny region of the quasar, perhaps a hotspot in its accretion disk or a dense cloud in its broad emission line region, is suddenly and dramatically magnified. The overall brightness of the quasar image we see flickers in a unique way, but the real magic is in the details. Because the accretion disk and the broad line region have structure, they are not uniform points of light. Different parts are magnified at different times as the star moves. By meticulously decoding these subtle, complex flickers in the light curve, astronomers can perform a kind of cosmic tomography. They can map structures in the quasar's heart that are trillions of times smaller than any telescope could ever hope to see directly. We can infer the size of the accretion disk, measure how hot it is at different distances from the black hole, and even probe the motion and distribution of gas clouds in the broad line region. It is as if nature provided us with a microscope made of gravity and motion, allowing us to study the fine print on a postage stamp from 1,000 miles away. These microlensing events are transient and unpredictable, but when caught, they offer a priceless, high-resolution glimpse into the engine room of a quasar, revealing details that would otherwise be lost in the blinding glare of distance. This gravitational maze does not obscure the truth, it magnifies it, one wandering star at a time. Gravity's lens can reveal a quasar's hidden structure, but sometimes the engine room itself holds a secret. What if the monstrous heart beating at the center of a galaxy is not one heart but two, This leads us to our ninth bizarre phenomenon, the cosmic matryoshka, binary supermassive black holes. We have long known that galaxies collide. The universe is a violent dance, and when two spiral galaxies merge, their stars mingle into a new, larger elliptical galaxy. But what happens to their central black holes, each millions or billions of times the mass of our Sun? The theory is both simple and staggering. They do not vanish. They sink toward the new common center of gravity, beginning a slow cosmic waltz. For a time, they might both be active, both feeding from the chaotic influx of gas stirred up by the merger. We could, in essence, have a quasar with two engines. Finding definitive proof of such a pair is incredibly difficult, their signatures blurred into a single point of light from billions of light years away. Yet astronomers are hunting for the bizarre clues. One telltale sign could be a strange, regular flicker in the quasar's light curve. As the two black holes orbit each other, their accretion disks might be periodically disrupted, or one might regularly block our view of the other, causing a predictable dip in brightness every few years. Another potential signature is even more dramatic: helical jets. If one of the black holes is launching a jet, but the entire system is wobbling due to the gravitational pull of its companion, that jet would not be a straight beam. It would corkscrew through space like water from a spinning garden hose, leaving a twisted trail across the cosmos. Recent observations have provided tantalizing hints. Some quasars show light curves with repeating patterns. Others have jets with bizarre, sinuous kinks that are hard to explain with a single, stable black hole. There is even a candidate system where the broad emission lines in the spectrum appear to be double, as if coming from two separate, fast-moving sources. The ultimate fate of such a binary is written in the fabric of space-time itself. As they orbit, they lose energy by rippling space-time, emitting gravitational waves. Over eons, this loss causes them to spiral inward, closer and closer, until finally they merge in a cataclysm that dwarfs all others. The collision of two supermassive black holes would shake the universe, releasing a burst of gravitational waves so powerful it would briefly outshine the combined light of every star in the cosmos. We have not yet directly detected such an event, but observatories are listening for the echo of that ultimate cosmic crash. This possibility transforms our view of the active nucleus from a single monster into a dynamic, dueling system, a final, violent chapter in the story of a galactic merger. It suggests that the most brilliant beacons in the sky might sometimes be powered by a dance of two shadows, slowly tightening their embrace until only one remains. That dueling heart of a binary black hole would be a spectacular rarity, but there is a far more common and fundamental divide among quasars themselves. One of the oldest and most persistent mysteries is why some quasars are cosmic radio stations, blasting their presence across the universe, while others are shrouded in radio silence. This is the 10th bizarre phenomenon, the great schism between radio-loud and radio-quiet quasars. For all their brilliance, only about 1 in 10 quasars produces those colossal, focused jets that scream in radio wavelength. The overwhelming majority are considered radio-quiet, their phenomenal energy output concentrated almost entirely in visible light, ultraviolet, and X-rays. They are still monstrously powerful, but they lack the universe-spanning radio lances of their louder cousins. So what makes one engine roar and another whisper? The leading hypothesis points to the black hole spin. A supermassive black hole is not just a mass, it is a dynamo. The faster it spins, dragged by the swirling accretion disk, the more energy it can extract from the infalling matter, and the more powerfully it can twist the magnetic fields anchored in its disk. Think of it like a spinning top. A fast spinning top is stable, energetic, and can interact strongly with its surroundings. A slow or non-spinning top simply sits there. In this view, a rapidly spinning black hole acts as a powerful battery, winding magnetic field lines into a tight, organized structure that can launch and collimate those relativistic jets. A black hole with little to no spin simply lacks the rotational energy to power such a focused, long-lived outburst. Its magnetic fields may be weaker or more chaotic, leading to energy being dissipated as heat and light in the accretion disk rather than being funneled into jets. Yet this elegant idea is far from proven. Observations are incredibly challenging. Measuring the spin of a black hole billions of light years away is an indirect and difficult art. Some data suggests radio-loud quasars might inhabit denser galactic environments, perhaps where mergers are more common, which could feed gas in a way that spins up the central black hole. Their host galaxies also tend to be giant ellipticals, the products of galactic collisions, rather than the spiral galaxies that often house radio-quiet quasars. This hints that the history of the galaxy itself, its violent past of mergers and acquisitions, might determine the character of its central monster. Is the difference truly fundamental, a question of the engine's very blueprint? Or is it simply a phase, a temporary state dictated by the available fuel and the black hole's recent history? Could a radio-quiet quasar become radio-loud if a fresh influx of gas spins up its black hole? We do not yet know. This great divide reminds us that for all we have learned, the ignition switch for the universe's most powerful engines remains hidden, a simple toggle between silence and a scream that echoes across the cosmos. That radio silence from most quasars is profound, but there is another signal, one that has traveled for almost the entire age of the cosmos. The light from the most distant quasars is a message from the universe's infancy, a time traveler's beacon. This is our 11th bizarre phenomenon, the existence of high redshift quasars. To understand why they are so shocking, you must grasp what redshift means. As the universe expands, it stretches the very fabric of space, and the light traveling through that space gets stretched along with it. The longer the journey, the more the light is stretched, shifting its color toward the red end of the spectrum. A high redshift means an object is incredibly far away, and therefore we are seeing it as it was in the very distant past. Astronomers have now found quasars with redshifts so high that their light left them when the universe was less than 700 million years old. That is a mere 5% of its current age. These are not just ancient objects, they are fully formed cosmic monsters from a time when the first galaxies were still assembling. And that is the heart of the paradox. We see quasars powered by supermassive black holes with masses of over 1 billion suns, already shining with ferocious brilliance in a universe that had just begun. How is this possible? How does a black hole grow to such an unimaginable size in what is, cosmically speaking, the blink of an eye? This is the seed black hole problem, one of the greatest outstanding puzzles in astrophysics. Did these giants start from enormous seeds? One theory suggests that in the primordial universe before the first stars ignited, vast clouds of pure hydrogen could have collapsed directly under their own gravity, bypassing the star stage entirely and forming black holes tens of thousands of times the mass of our Sun. These would be ready-made heavyweights, giving them a massive head start on growth. The other leading idea is that the first generation of stars, known as population 3 stars, were behemoths hundreds of times more massive than our Sun. They would have lived fast, died young, and left behind black hole remnants of perhaps only a few hundred solar masses. To grow from that to 1 billion solar masses in under 1 billion years would require a feeding frenzy of almost constant maximum rate accretion, pushing the theoretical limits of physics. We do not yet know which path, or perhaps a combination of both, nature took, but these distant quasars are more than just problems, they are priceless probes. Their brilliant light acts as a cosmic flashlight, illuminating everything between them and us. As that light journeys for billions of years, it passes through the diffuse gas that filled the early universe. By analyzing the subtle absorption lines imprinted on the quasar spectrum, astronomers can map the distribution and state of that ancient hydrogen. This is how we study the epoch of reionization, the universe's great dawn. After the Big Bang, the cosmos was a dark, opaque fog of neutral hydrogen. Then the first stars and galaxies and quasars like these switched on. Their intense ultraviolet radiation began to strip electrons from the hydrogen atoms, ionizing the fog and making the universe transparent to light. The light from a high redshift quasar carries the fingerprint of that final era of cosmic clearing. In the deepest images from telescopes like Hubble and James Webb, these quasars appear as single, brilliant pinpricks in a field of faint, infant galaxies. They are lighthouses on the shores of time, beacons from an era of first light, and their very existence forces us to rewrite the story of how the cosmos built its most mysterious structures from the darkness. Those ancient beacons do more than illuminate the early cosmos. They might also be firing bullets at us. The most energetic particles in the universe are not born in supernova or colliding stars. They come from somewhere far more extreme. This is the 12th bizarre phenomenon, the cosmic ray factory of active galactic nuclei. We are talking about ultra-high energy cosmic rays, single protons or atomic nuclei, hurtling through the void with energies so incomprehensibly high they carry the punch of a major league fastball, all packed into a single subatomic particle. Their energy is millions of times greater than anything our most powerful machine, the Large Hadron Collider, can produce. For over a century, their origin has been one of astrophysics' greatest mysteries. Where in the universe is there a natural accelerator of such impossible power? The prime suspect has long been the relativistic jets screaming from active galactic nuclei. Think of the environment within one of those jets. It is a maelstrom of magnetized plasma moving at almost the speed of light, riddled with shock waves and turbulent magnetic fields that stretch for thousands of light years. This creates the perfect natural particle accelerator. A proton caught in this chaos can bounce back and forth across a shock wave front, trapped by the intense magnetic fields. With each crossing, it gains a little more speed, a little more energy, like a ball being ping-ponged between two converging walls. In the vast length of a jet, this process can continue for eons, accelerating that single proton to velocities so extreme its energy becomes almost unimaginable. Eventually, the magnetic trap fails, and the particle is ejected into intergalactic space like a bullet from a cosmic rifle, destined to wander the voids for millions or billions of years. The detective work to prove this is a monumental challenge. These particles are incredibly rare, striking Earth's atmosphere only about once per square kilometer per century. When they do, they create a spectacular air shower, a cascade of secondary particles that our ground-based observatories can detect. But the particle itself is neutral electrically, so it does not travel in a straight line. The galactic and intergalactic magnetic fields it passes through bend its path, scattering its trajectory like a pinball. By the time it reaches us, we cannot simply look back along a straight line to see where it came from. It is a crime scene with a twisted, washed-away trail. However, in recent years, pieces of the puzzle have begun to fit. When astronomers correlate the arrival directions of the very highest energy cosmic rays with maps of the sky, a pattern tentatively emerges. They seem to point back toward regions of space outside our own galaxy, and their distribution is not random. Some of the most compelling associations are with powerful blazars, those active galactic nuclei with their jets pointed directly at us. In one landmark case, a single ultra-high-energy cosmic ray was traced back to a void in the large-scale structure of the universe, a seemingly empty desert. But sitting in that desert, billions of light-years away, was a ferocious blazar flaring at just the right time. It was a cosmic smoking gun. The evidence is still statistical, a matter of probabilities rather than certainties, but the case grows stronger. If confirmed, it means the most violent engines in the cosmos are not just beacons of light, but also stealthy artillery, silently bombarding the universe with particles of ultimate power. Every so often, one of those bullets fired from a monster a billion years ago ends its journey in a flash of light in our own sky. The universe's most powerful artillery also offers a paradox of perception. For decades, astronomers noticed a strange and counterintuitive pattern among blazars, those quasars with jets aimed directly at Earth. It became known as the blazar sequence, and it presents our 13th bizarre phenomenon, the illusion of size. Here is the puzzle. When you plot the brightness of these objects across the entire electromagnetic spectrum, from radio waves to gamma rays, they do not all look the same. The most luminous, overwhelmingly powerful blazars tend to have their peak emission in the lower energy bands, like radio and infrared light. Meanwhile, the fainter, less powerful blazars have their brightest emission in the high-energy X-ray and gamma-ray parts of the spectrum. This is deeply odd. In most things, more power means more heat. A bigger fire is hotter, not cooler. Yet here, the cosmic rule seems inverted. The implication is startling. It suggests that the most monstrous engines with the highest total power output might actually possess larger, cooler accretion disks. The weaker blazars, by contrast, might be powered by smaller, hotter, and more compact disks. Think of it like two campfires. One is a vast, sprawling bed of glowing coals. It produces immense total heat, but the temperature at any one point is relatively modest, radiating mostly in the infrared warmth you feel on your skin. The other is a fierce, concentrated blowtorch flame. It is far smaller in total size and puts out less total energy, but at its heart, it is searingly hot, emitting the piercing blue light of a much higher temperature. The blazar sequence hints that the quasar family might operate on a similar principle. The truly colossal black holes with immense gravitational reach might draw matter into a broader, more extended accretion disk. The infalling gas has more room to spread out and radiate its energy away as it spirals slowly inward, resulting in a cooler overall temperature that peaks in infrared light. A smaller black hole with a tighter gravitational grip might compress its accretion disk into a smaller, denser, and far hotter maelstrom, which then shines most brightly in X-rays. But is this sequence a fundamental law of physics, or is it a trick of our vantage point? This is where the debate gets fierce. Some scientists argue it is a real evolutionary sequence. Perhaps as a blazar consumes fuel over cosmic time, its accretion disk evolves, changing in size and temperature, and this sequence is a snapshot of different life stages. Others propose it is a selection effect, a bias imposed by our telescopes. The most luminous objects are so incredibly bright they drown out our ability to see their high-energy emission clearly, while the fainter ones are only detectable when they are in a hot, flaring state. We might be comparing a giant's steady roar to a dwarf's occasional scream, mistaking volume for temperature. Unraveling this illusion is crucial. If the sequence is real, it gives us a direct way to gauge the physical scale of an invisible engine billions of light years away, simply by analyzing the color of its brilliance. It would be a cosmic thermometer and ruler combined, but if it is a mirage, it means our understanding of how these engines scale with power is still deeply flawed. The answer lies in painstaking observations, collecting the full spectral fingerprints of thousands of these objects to see if the pattern holds or crumbles. It is a reminder that in the study of quasars, even the most basic relationships between power and appearance can be a hall of mirrors, challenging us to distinguish the true nature of the beast from the shadows it casts. The color of a blazar's brilliance hints at the engine scale, but what is the engine itself? We have spoken of spinning black holes and superheated accretion disks, but there is an invisible architect behind the most powerful outburst. This is our 14th bizarre phenomenon, the magnetic dynamo. To truly grasp the quasar's power, we must move beyond gravity and heat and into the realm of force fields. The sheer violence of the accretion disk and the spin of the black hole would be chaotic and unfocused without a guiding hand. That hand is magnetism. Imagine the swirling disk not just as hot gas, but as a sea of electrically charged particles. This motion on a cosmic scale generates immensely powerful magnetic fields. Now picture those magnetic field lines as elastic threads anchored in the disk. As the disk rotates at fantastic speeds, it drags these threads with it, winding them up tighter and tighter around the black hole like the rubber band on a toy airplane. This winding stores colossal energy, creating tension that must eventually snap. But there is an even more exotic source of power. Around a spinning black hole lies a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Nothing can stand still here. It is like being caught in a cosmic whirlpool. According to a theory known as the Blandford-Zienagic process, magnetic field lines can become anchored in this swirling space-time. As the black hole spins, it twists these field lines into a coiled spring of pure energy. This process can literally extract rotational energy from the black hole itself, converting the spin of the abyss into a focused electrical current that flows out along the magnetic field lines. It acts like a universe-sized electric generator, with the spinning black hole as its rotor and the magnetic fields as its wiring. This stolen spin energy is a prime candidate for launching and powering those relativistic jets. There is a companion theory, the Blandford-Payne process, which focuses on the accretion disk itself. Here, the magnetic fields anchored in the outer disk are spun by its rotation, flinging material outward like beads on a rotating wire. This can power slower, wider outflows from the disk. Think of the two processes as different gears in the same cosmic machine. Blandford-Payne might be the lower gear powered by the disk's rotation, responsible for broader winds. Blandford-Zienagic is the ultimate overdrive, tapping directly into the black hole's spin to forge the ultra-fast, focused jets that punch into intergalactic space. The terrifying beauty of these ideas is that they turn the black hole from a passive sinkhole into an active dynamo. It is not just eating, it is working. Its rotation, combined with the magnetic fields forged in the surrounding chaos, creates a circuit that can light up galaxies. Yet for all its theoretical elegance, the magnetic dynamo remains shrouded in mystery. We cannot see magnetic fields directly from billions of light-years away. We infer their presence from the ordered structure of the jets and the polarization of light. Understanding exactly how these fields form, how they become so intensely organized, and which process dominates in which quasar, is one of the great frontiers of astrophysics. It suggests that the true power of the monster does not lie in the darkness at its center, but in the invisible, twisting force fields that harness that darkness. The magnetic dynamo may forge the quasar's power, but its true legacy is written in the wind. These are not gentle breezes, but galactic-scale hurricanes, and they reveal the quasar as a cosmic pollinator. We glimpsed this earlier with broad absorption line winds, but the full picture is even more transformative. The intense radiation and the powerful outflows from an active nucleus act like a colossal bellows, pointed directly at the raw fuel of the galaxy itself. This process, called quasar feedback, is one of the most important ideas in modern cosmology. It answers a fundamental question: why are there not infinitely large galaxies filled with ancient stars? The quasar itself provides the stop switch. As the furious winds blast outward, they slam into the vast reservoirs of cold molecular gas scattered throughout the host galaxy. This is the very material needed to collapse and form new stars. The quasar's wind does not gently nudge this gas. It heats it to millions of degrees, disperses it into a thin, hot fog, or in the most extreme cases, blows it completely out of the galaxy and into the vast intergalactic voids. The stellar nursery is effectively sterilized. Star formation across the entire galaxy can slow to a crawl or cease entirely. This is how a monster feasting at the galaxy's heart regulates the growth of its own home. But the story does not end there. This violent expulsion has a creative side. The gas being blown out is not just pure hydrogen and helium. It is enriched with heavy elements: carbon, oxygen, iron, silicon. forged in the hearts of earlier generations of stars and now churned up by the quasar's fury. As this metal-rich material is catapulted into intergalactic space, it seeds the barren voids with the building blocks for future planets and even life. The quasar, in its rage, becomes a cosmic pollinator, scattering the essential ingredients for complexity far beyond its own borders. Astronomers have seen the evidence for this spectacular process. Using telescopes like the Chandra X-ray Observatory, they have observed enormous cavities, vast bubbles carved out of the hot gas that surrounds massive galaxies in clusters. These bubbles, often aligned with the direction of radio jets, are the fossil imprints of ancient quasar outbursts. They are the ghosts of galactic winds that blew millions of years ago. In other observations, spectra reveal the shock fronts where these supersonic outflows smash into the surrounding medium, heating it and lighting it up like a cosmic neon sign. This phenomenon reshapes our entire view of the quasar's role. It is not a passive parasite nor a mere spectacle. It is an active and dominant architect. The quasar's brief, brilliant phase of hyperactivity may determine the ultimate fate of its galaxy, setting its final mass, shaping its structure, and deciding when its star-forming days are over. It connects the smallest, most violent region of space-time to the largest scales of cosmic evolution. The monster does not just live in the galaxy, it builds it, and then it decides when the construction must end. The quasar's wind scatters the seeds of future worlds, but its light carries a more immediate secret. Every color in its brilliant glow is a coded message, a spectral fingerprint that reveals the hidden anatomy of the monster. This is our 16th bizarre phenomenon, the language of light written in broad and narrow emission lines. When astronomers pass a quasar's light through a spectrograph, they do not see a simple, smooth rainbow. They see a forest of bright spikes and dark troughs superimposed on the continuum. This is the object's unique fingerprint, and it is far more complex than that of any star. The most prominent features are the bright emission lines glowing at specific colors, but look closer and you will see they are not all the same. Some are incredibly broad, smeared across a wide range of colors. Others are sharp and narrow, like precise scratches on the surface of the spectrum. This split personality points directly to two distinct regions around the black hole, each telling a different part of the story. Close to the inferno, within just a few light days or weeks of the black hole, lies the broad line region. Here, clouds of hydrogen, helium, and heavier elements are caught in the black hole's fierce gravitational grip. They are not orbiting sedately, they are screaming around at velocities of thousands of kilometers per second, some moving toward us, some away. This frantic motion is the key to the broad lines. The Doppler effect, the same phenomenon that makes a siren's pitch change as it passes, stretches and compresses the light from these clouds. Gas moving away from us has its light redshifted to longer wavelengths. Gas moving toward us is blue-shifted. Because the clouds are moving in all directions at these incredible speeds, their individual emission lines get smeared together into a single, fat, broad hump in the spectrum. The width of that hump is a direct measure of the cloud's velocity, which in turn tells us about the black hole's mass at the center of the chaotic dance. Farther out, light years from the central engine, lies a calmer but still illuminated realm, the narrow line region. This gas is still energized by the quasar's intense radiation, but it is no longer dominated by the black hole's direct gravitational pull. It moves with the slower, more orderly rotation of the host galaxy itself, at speeds of just a few hundred kilometers per second. With less extreme motion, the Doppler broadening is minimal. The emission lines from this region remain sharp and narrow, like precise signatures on a document. The beauty of this two-part fingerprint is that it allows astronomers to perform cosmic forensics. By measuring the width of a broad hydrogen line, they can calculate the mass of the invisible black hole itself. It is like listening to the roar of a crowd around an unseen singer. The intensity and chaos of the sound tell you how powerful the central attraction must be. Meanwhile, the ratios between different narrow lines act as a chemical probe. They reveal the density, temperature, and even the chemical composition of the gas in the host galaxy, showing if it is enriched with the elements forged in generations of stars. This spectral fingerprint, with its broad chaos and narrow clarity, is a Rosetta Stone. It allows us to weigh the unseeable, map the structure of the invisible, and read the history of an entire galaxy in the colored lines of a single, brilliant point of light. That spectral fingerprint is a detailed message, but what is the final fate of the matter that sends it? The material screaming in the broad line region is on a one-way journey toward an absolute boundary, the event horizon. And here, quasars connect to a firestorm raging at the very foundations of physics itself. This is the 17th bizarre phenomenon, the dark heart and the black hole information paradox. At its core, this is a battle between two pillars of modern science, general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, describes black holes beautifully. It says the event horizon is a point of no return. Anything that crosses it, a book, a star, an entire spaceship, is lost to our universe forever. All the intricate information about that object, the arrangement of its atoms, its history, its very identity, is crushed into the singularity and disappears. But quantum mechanics, the rules governing the very small, has a fundamental law: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. So, which is it? Does the universe allow for permanent information loss at a black hole's horizon? Or does it somehow preserve that information in a way we cannot yet see? This is the paradox, and it suggests one of our most successful theories is incomplete. Quasars and active galactic nuclei are not just bystanders to this puzzle, they are the primary laboratories. The intense radiation we see, from X-rays to radio waves, is the last reliable signal from matter before it approaches the point of no return. The broad emission lines are the final, Doppler-smeared scream of atoms being torn apart. The jets may be the last organized structures that escape the black hole's grip. By studying this output with extreme precision, astronomers and physicists hope to find subtle clues encoded in the light. Could there be faint imprints like quantum hair left on the radiation that tell us something about the information of the infalling material? The chaotic flickering of the accretion disk might not just be random noise, but a complex signal of information being processed and perhaps even encoded at the horizon itself. Some theoretical work even suggests that the event horizon might not be the perfectly smooth membrane relativity predicts, but a firewall of unimaginable energy or a fuzzy quantum structure that somehow preserves information. While we cannot see past the horizon, the furious activity just outside it in an active galactic nucleus is our closest vantage point. Each brilliant quasar is more than a cosmic engine. It is a front-row seat to the greatest conflict in theoretical physics, a place where the fabric of reality is stretched to its breaking point. The answers, if they come, will not arrive from a chalkboard alone, but from decoding the last cries of matter vanishing into the dark, captured in the light of these distant beacons. That firestorm at the event horizon is a profound mystery, but quasars may hold a key to solving a different cosmic puzzle, one that defines the fate of the universe itself. Our 18th bizarre phenomenon asks if these chaotic monsters can become cosmic yardsticks, reliable rulers for measuring the vastness of space. For decades, astronomers have relied on what they call standard candles, objects of known intrinsic brightness. By measuring how dim they appear from Earth, we can calculate their distance. The most famous of these are Type Ia supernova, stellar explosions so uniform they lit the path to the discovery of dark energy. But supernovae are fleeting. They flare and fade to peer deeper into the past, to map the expansion of the universe when it was half its current age or younger. We need a beacon that shines continuously, something visible across the entire cosmos. Quasars, with their staggering brightness, seem like the perfect candidate. There is just one enormous problem: they are infamously variable. No two quasars are exactly alike, and their brightness dances unpredictably over time. A brilliant quasar could be a relatively modest engine seen up close, or a true monster lurking at the edge of time. How do you calibrate a ruler that keeps changing its length? The answer may lie not in the quasar's total light, but in its internal structure, specifically the relationship between the size of the broad line region and the quasar's luminosity. This is where a technique called reverberation mapping comes in. Think of the central accretion disk as a brilliant flashbulb, and the surrounding clouds of the broad line region as surrounding walls. When the flashbulb flares, it takes time for that light to travel out, hit the gas clouds, and make them glow in response. By meticulously monitoring the quasar's light, astronomers can detect a time delay between a flare in the continuum light from the disk and the corresponding flare in the broad emission lines from the clouds. That delay is a direct measure of the distance the light traveled, telling us the physical size of the broad line region. Here is the crucial part. That measured size appears to have a predictable relationship with the quasar's overall luminosity. A bigger, more luminous quasar tends to have a larger broad line region. If this relationship is tight and universal, it gives us a way to measure a quasar's true power. Once we know its true power from the size of its broad line region, we can compare that to how bright it appears in our sky and calculate its distance just like a standard candle. It is a cosmic echolocation technique, using light delays to turn a chaotic monster into a precise measuring tape. The promise is staggering. Quasars are visible out to the very earliest epochs of galaxy formation, far beyond the reach where we can reliably find supernova. If perfected, they could trace the history of cosmic expansion from the universe's wild youth through its middle age and into its accelerated old age, all with a single class of object. They could provide an independent check on dark energy, perhaps even revealing if its strength has changed over cosmic time. The quest is ongoing, a massive international effort to monitor thousands of quasars and refine the calibrations. The challenge is immense, as the reverberation signals are subtle and the physics of the broad line region is complex. But if this method can be tamed, these most violent and unpredictable engines could become our most precise guides to the geometry of everything. The quest to turn quasars into cosmic yardsticks reveals a luminous universe, but our census of these monsters has long been incomplete. For every brilliant beacon we see, there may be another lurking in the shadows, cloaked by its own fuel. This is the 19th bizarre phenomenon, the phantom population of obscured active galactic nuclei and the cosmic X-ray background. Imagine the sky not just in visible light, but as it appears in high-energy X-rays. For decades, sensitive X-ray telescopes detected not just the brilliant points of known quasars, but a persistent, diffuse glow coming from every direction. This was the cosmic X-ray background, a mysterious fog of high-energy light that permeated the universe. Its origin was one of astronomy's great unsolved puzzles. Where was all this X-ray light coming from? The leading suspect was a vast number of hidden active galactic nuclei, their brilliant cores completely veiled by thick shrouds of dust and gas. In visible light, these objects are invisible, their light absorbed and transformed into infrared heat by the cosmic soot, but X-rays are far more penetrating. They can punch through those thick veils, offering a glimpse of the searing engine within. The challenge was to resolve that diffuse X-ray fog into individual points of light. It required a new generation of X-ray telescopes with unprecedented sensitivity and resolution. The breakthrough came with observatories like Chandra and XMM Newton. They stared at seemingly blank patches of sky, and the fog dissolved. It resolved into millions upon millions of individual, point-like sources. The vast majority were not stars in our own galaxy, but distant, obscured active nuclei. This was a monumental triumph. It revealed that for every classic, brilliant quasar we see, there could be several more that are hidden from our optical view. The universe's population of supermassive black holes was far larger and more active than we had ever imagined. These obscured monsters are not merely curiosities, they are a critical phase in the life cycle of a galaxy. The thick shroud likely represents the peak of the feeding frenzy, when so much gas and dust are funneling toward the black hole that the central engine is literally buried in its own fuel supply. It is a cosmic cocoon stage where the monster is growing most rapidly, hidden from view. Infrared telescopes like Spitzer and James Webb provide the complementary view, seeing the heat glow from that obscuring dust. By combining X-ray and infrared data, astronomers can peer through the veil and estimate the true power of the hidden engine. This phantom population solves the mystery of the X-ray background and rewrites the story of black hole growth. It suggests that the most dramatic growth spurts of supermassive black holes happen not in brilliant, visible outbursts, but in hidden, dusty feasts shrouded from the optical universe. We are only now beginning to take a true census of the monsters in the dark, realizing that what we see shining is merely the tip of a vast, shadowy iceberg. That phantom population remains hidden, but for the brilliant beacons we can see, astronomers have crafted a brilliant technique to weigh the invisible monster at their heart. It is called reverberation mapping, and it turns the chaotic broad line region into a precise cosmic echo chamber. The principle is elegant in its simplicity. At the center, the superheated accretion disk flares unpredictably, its brightness surging in a burst of ultraviolet and optical light. This flare acts like a sudden flash from a lighthouse. That light does not just travel straight to us, it also floods outward in all directions, illuminating the swirling clouds of gas in the broadline region that orbit much farther out. Those clouds absorb the high-energy light and re-emit it at their own specific colors, creating the bright, broad emission lines in the spectrum, but there is a delay. Light has a finite speed. It takes time for that initial flash from the disk to travel the vast distance, often trillions of kilometers out to the gas clouds. Astronomers monitor the quasar's light for months or years, watching patiently. They track two things simultaneously: the flickering of the continuum light from the disk itself and the flickering of the broad emission lines from the surrounding gas. What they find is a telltale echo. A sharp flare in the disk's light is followed days or weeks later by a corresponding flare in the hydrogen or other emission lines. That time delay is a direct measurement. It tells us exactly how long the light took to travel from the central engine out to the gas clouds. Since we know the speed of light is constant, we can instantly calculate the physical distance between the black hole and that part of the broad line region. We are not just guessing the size, we are measuring it with a stopwatch made of photons. But the clouds are not in a neat shell. They orbit the black hole in a complex, turbulent swarm. By studying how the delay changes for different emission lines, which come from different types of gas at different distances, astronomers can begin to map the three-dimensional geometry of this entire region. They can discern if it is a spherical halo, a flattened disk, or a chaotic inflow of material. Once the size and structure of the broadline region are known, the final, crucial step is to weigh the black hole. This is where an ancient law of orbital motion, Kepler's law, comes into play. The gas clouds are in orbit, held by the black hole's gravity. The width of the broad emission lines tells us how fast those clouds are moving. The broader the line, the higher the velocity. Kepler's law gives a direct relationship. If you know the size of an orbit and the speed of the object within it, you can calculate the mass of the central object holding it there. It is the same principle we use to weigh the Sun by measuring Earth's orbit. Reverberation mapping provides the orbit size from the light echo, and the spectrum provides the orbital speed from the line width. Put them together and you have a direct measurement of the supermassive black hole's mass, an invisible giant weighed by the delayed whispers of its own light. This technique has transformed quasars from brilliant mysteries into calibrated laboratories. It confirms that the monsters powering these engines truly are millions or billions of solar masses, and it provides the foundational relationship that might one day turn quasars into the universe's ultimate measuring tapes. Reverberation mapping weighs the monster, but what is happening inside the feeding frenzy itself? The accretion disk is not a serene, steady whirlpool. It is a battlefield of competing forces, prone to sudden and violent revolutions. This internal chaos drives our 21st bizarre phenomenon, the extreme environment of disk instabilities and state changes. The stability of the entire luminous engine hangs on a delicate and often broken balance. Within the disk, two primary forces are in a constant tug of war. Gravity pulls matter inward, compressing and heating it. At the same time, the intense radiation produced by that heating pushes outward, a phenomenon called radiation pressure. In most steady situations, these forces reach an equilibrium, but in the most luminous quasars, where the accretion rate is extraordinarily high, radiation pressure can become the dominant force. And here, theory predicts catastrophe. A radiation pressure-dominated disk is inherently unstable. Imagine trying to balance a marble on the crest of a steep hill. A tiny nudge in any direction sends it careening off. In the disk, a small, local increase in temperature causes a surge in radiation pressure, which pushes material outward, momentarily lowering the density and allowing that region to cool. But as it cools, the radiation pressure drops, gravity wins back control, and matter comes crashing back in, heating up again and restarting the cycle. This creates a feedback loop of violent pulsations, where entire sections of the disk may brighten and dim in chaotic, runaway oscillations. These are not the small flickers of magnetic flares, but potential engine-wide convulsions that could explain some of the most dramatic, changing-look transitions. The disk might literally tear itself apart from the inside out, switching between a bright, puffed-up, radiation-dominated state and a faint, cool, gas-pressure-dominated state. We see scaled-down versions of this drama playing out in our own galactic backyard, in systems called X-ray binaries. These are stellar mass black holes or neutron stars feeding on a companion star. Remarkably, they display clear state transitions. They can spend years in a quiet, hard X-ray state with a faint disk and powerful jets. Then, as more gas streams in, they may abruptly switch to a soft, luminous state where the disk shines brilliantly in thermal radiation and the jets shut off entirely. The physics is analogous, just on a million-fold smaller scale. The instabilities in these small systems are like a roaring campfire we can study up close, giving us a template for understanding the continent-sized wildfires blazing in quasars. For the supermassive black hole, a major state change could mean the difference between being a brilliant quasar and a dim, dormant giant. It suggests the monster's appetite is not just about how much food falls in, but how that food is served. A sudden, gorging influx might trigger the unstable, radiation-dominated mode, lighting the beacon. Once that chaotic feast is digested, the disk could collapse back into a stable, quiet mode and the beacon winks out. The engine's very personality is written in the unstable physics of its furnace, a place where light itself can become so powerful it destabilizes the machine that creates it. That unstable engine, blazing in its isolated fury, does not shine into an empty void. Its light travels for billions of years through a universe that is far from empty. It passes through a hidden architecture, a vast cosmic web of dark matter and diffuse gas that connects all galaxies. And here, the quasar becomes something more than a monster. It becomes a tool, a flashlight in the cosmic dark. This is our 22nd bizarre phenomenon, the quasar as an intergalactic web illuminator. The space between galaxies is not a perfect vacuum. It is threaded with tenuous filaments of primordial hydrogen and helium, the leftover material from the Big Bang that never collapsed into stars. This is the cosmic web, the largest structure in the universe, and it is incredibly faint, almost impossible to see directly. But a quasar's brilliant beam gives us away. Imagine standing in a dense, dark forest at night, holding a powerful spotlight pointed at a distant observer. Every tree and branch between you and that observer would cast a sharp, black shadow against the light. The quasar does the same thing on a cosmic scale. As its intense light journeys toward Earth, it passes through these filaments of intergalactic hydrogen. The hydrogen atoms absorb very specific colors of that light, imprinting a forest of dark absorption lines on the quasar spectrum. Astronomers call this the Lyman alpha forest. It is not one line but thousands, a dense thicket of shadows. Each line corresponds to a different cloud or filament of hydrogen at a different distance along the line of sight. Because the universe is expanding, each cloud is redshifted by a different amount. The pattern is a barcode, a one-dimensional core sample of the universe's structure between us and the quasar. By analyzing this intricate forest of lines, astronomers can perform a kind of cosmic tomography. They can map the density, temperature, and distribution of the gas that makes up the cosmic web. They can see where it clumps into denser knots, the future sites of galaxy clusters, and where it stretches into vast, empty voids. This turns a single brilliant point into a probe that dissects the entire cosmos along its line of sight. The most distant quasars are the most valuable flashlights because their light has passed through more of the young universe. They allow us to study the cosmic web when it was first assembling, revealing how gravity drew matter together from an almost smooth beginning into the grand filamentary structure we see today. The quasar, in its violent brilliance, thus serves a higher purpose. It illuminates the invisible scaffolding upon which all galaxies, including its own, are hung. It reveals that the monster is not separate from the cosmos, but a product of it, and now a guide to understanding its deepest architecture. That flashlight reveals the cosmic web, but the quasar's jets are also firing something far more elusive into the void. In September 2017, a single ghostly particle struck a block of ice deep under the South Pole. This was not a cosmic ray, but a neutrino, an almost massless particle that barely interacts with matter. Trillions pass through your body every second, leaving no trace, but this one was special. It carried an energy millions of times greater than any particle in the Large Hadron Collider. The Ice Cube Neutrino Observatory captured its arrival, and astronomers raced to trace its path back across the cosmos. Their search led them to a monster already under watch, a blazar known as TXS-0506 plus 056, flaring brilliantly 4 billion light-years away. This was the first time a high-energy neutrino had ever been traced to a specific source beyond our own galaxy. The implications were staggering. For decades, the origin of ultra-high-energy cosmic rays had been a mystery, with blazar jets as the prime suspect. But cosmic rays are charged, their paths bent by magnetic fields, obscuring their origin. Neutrinos are neutral ghosts. They travel in perfectly straight lines, unaffected by magnetic fields, pointing a direct, unwavering finger back to their source. This single particle was the smoking gun. It proved definitively that the turbulent hearts of blazar jets are not just accelerators of light and protons, but also of these ghostly messengers. The process is thought to be brutal. Within the jet's magnetized chaos, protons are accelerated to near light speed. Some of these protons then collide with photons or other particles, creating a cascade of secondary particles, including pions. These pions then decay, producing, among other things, high-energy neutrinos. The detection of that neutrino from TXS-0506 meant we were witnessing the byproducts of the most powerful particle collisions in the universe. This event marked a triumph of multi-messenger astronomy, a new era where we no longer rely on light alone. We now combine the story told by photons across all wavelengths with the signals from particles like neutrinos and the ripples in spacetime from gravitational waves. It is like understanding a storm by seeing the lightning, hearing the thunder, and feeling the rain. Each messenger carries different information. Light shows us the heat and structure. Neutrinos reveal the hidden hadronic processes, the sites of extreme particle acceleration. This single detection confirmed a century-old suspicion and opened a new window into the engine room. We are no longer just watching the monster's brilliant glare. We are now catching the invisible fallout from its most violent internal explosions. That ghostly neutrino was a direct signal from the particle accelerator within the jet, but some of the universe's most brilliant flares are born from a single catastrophic meal. We have watched quasars blaze for millions of years, but what happens when a dormant giant awakens for a brief, violent feast? This is the 24th phenomenon, the final whisper of a tidal disruption event. Here, a supermassive black hole, quiet and dark at the center of an otherwise normal galaxy, gets an unexpected visitor. A star, wandering too close on its orbit, crosses the black hole's Roche limit. At this boundary, the tidal force from the black hole, the difference in gravity between the star's near side and its far side, becomes stronger than the gravity holding the star itself together. The star does not simply fall in, it is ripped apart. In a process gruesomely termed spaghettification, the star is stretched into a long, thin stream of gas, like cosmic taffy pulled apart by an irresistible force. Roughly half of this stellar debris is flung out into the void on hyperbolic trajectories, lost forever. The other half remains bound to the black hole, forming a swirling, chaotic cloud that begins to rain down upon it. For a brief, spectacular moment, this infalling debris forms a temporary, superheated accretion disk around the once dormant black hole. The black hole, for all intents and purposes, becomes a temporary active galactic nucleus. It ignites with a flare that can outshine its entire host galaxy across the electromagnetic spectrum, from X-rays to visible light to radio waves. This is not a quasar which is fueled by a steady river of gas. This is a flashbulb event, the brilliant and fleeting scream of a single star being consumed. The physics is a bizarre, sped-up version of the quasar engine. The sudden influx of fresh fuel triggers all the familiar phenomena, but on a human timescale. Astronomers can watch the flare rise to peak brightness over weeks or months, and then slowly fade over the following months or years as the last of the stellar debris is swallowed or blown away. In some remarkable cases, these tidal disruption events have even been seen launching their own relativistic jets, proof that the same fundamental physics, a spinning black hole, a magnetized accretion disk, can spring into action almost instantaneously. These events are precious laboratories. They allow us to study the activation sequence of a supermassive black hole in real time from a cold start. We can watch the accretion disk form, heat, and begin to shine. We can measure how the outflowing winds develop and, if we are lucky, see the moment the jet launches. Each event is a chance to weigh the black hole, measure its spin, and understand how it interacts with its galactic environment when presented with a sudden, enormous gift of fuel. They are cosmic experiments repeated across the universe, where nature demonstrates the birth of an active nucleus right before our eyes. This final, brilliant whisper of a dying star is more than a spectacle. It is a masterclass in the life cycle of the monster, showing us that even the quietest giants are always waiting, just one stray star away from a catastrophic and illuminating rebirth. The ultimate fate of this brilliant chaos is a profound and elegant paradox. The quasar's fury contains the seeds of its own demise. For all its power to consume, its greatest legacy may be its power to starve. This is the grand, bizarre cycle that synthesizes nearly everything we have explored, the final feedback loop that shapes the cosmos. The monster, in its rage, eventually destroys the very conditions that created it. Through the colossal winds we saw in broad absorption lines and the immense energy of its jets, a quasar acts like a cosmic furnace with built-in fire extinguishers. As it feasts on the galaxy's gas, it simultaneously blasts that gas outward, heating it to millions of degrees or ejecting it entirely into intergalactic space. This process, quasar feedback, is not a minor side effect. It is the central plot twist in the story of galaxy evolution. Think of a roaring campfire that burns so fiercely it scatters all the remaining wood and kindling away from the hearth. The fire may blaze brilliantly for a time, but it ensures its own end by consuming its fuel and then removing any chance of a refuel. That is what a quasar does to its host galaxy. The cold, dense molecular clouds, the raw material for forming new stars, are either blown away or heated into a thin, hot plasma that cannot collapse. Star formation across the entire galaxy grinds to a halt. This explains one of astronomy's long-standing mysteries, the existence of red and dead elliptical galaxies. These are massive, smooth collections of ancient, red stars with almost no young, blue stars being born. They are galactic retirement homes. For years, we wondered what could possibly shut down star formation in something as vast as a galaxy. The answer is now clear: the brilliant, violent quasar phase in the galaxy's youth. After a major merger funnels vast amounts of gas toward the central black hole, igniting the quasar. That same quasar's energy output cleans out the galactic core. It creates the vast, hot bubbles we see in galaxy clusters and enriches the intergalactic medium with heavy elements. But it leaves the galaxy itself quiescent, its stellar population aging in peace. The evidence for this is written in a remarkable correlation. The mass of a galaxy's central, dormant supermassive black hole is not random. It is tightly linked to properties of the galaxy itself, specifically the mass and velocity dispersion of the stars in its central bulge. A more massive bulge hosts a more massive black hole. This correlation is too precise to be coincidence. It tells us the black hole's growth and the galaxy's growth are intimately connected, not as master and servant, but as partners in a violent dance. They co-evolve. The quasar feedback loop is the missing link. The more massive the black hole grows during its active phase, the more powerful its winds and jets become. The more powerful the feedback, the more effectively it shuts down star formation and regulates the final growth of the galactic bulge. The black hole, in essence, builds its own prison and then turns out the lights. It reaches a point where it has scoured its surroundings so clean that the river of fuel slows to a trickle. The accretion disk fades, the brilliant beacon winks out, and the monster returns to slumber, its mass now a permanent fossil record of the galaxy's most violent era. This is the ultimate bizarre phenomenon, a self-regulating engine of cosmic proportions. The quasar does not merely live within a galaxy. It sculpts it, determines its destiny, and then signs its own death warrant, leaving behind a silent giant in a quiet galaxy, a monument to the fury that once was. 25 glimpses into the heart of darkness, and yet we have only just begun. From superluminal mirages to cosmic ghosts, from binary black hole duels to the universe's own particle accelerators, each bizarre phenomenon peels back a layer of the same fundamental truth. Quasars and active galactic nuclei are not mere curiosities in a distant sky. They are the ultimate laboratories, places where gravity, magnetism, and quantum mechanics are pushed to breaking point under conditions we can never hope to recreate. Every mystery solved, like the illusion of faster-than-light motion or the unification of different galactic monsters, seems to reveal two more, pulling us deeper into the physics of the impossible. The story of the quasar is the story of the cosmos itself, a narrative of growth, feedback, and transformation written in the most violent penmanship imaginable. This journey does not end here. With every new telescope, we gain a sharper lens on this chaos. The James Webb Space Telescope is peering into the dusty cradles of the first quasars, watching them being born in the infant universe. The Vera C. Rubin Observatory will scan the entire sky every few nights, catching these giants in the act of flickering, flaring, and changing their nature before our eyes. We stand on the threshold of a new era of discovery, where the next great cosmic surprise is not a matter of if but when. The universe's most brilliant monsters still have secrets to whisper, and their final roars have yet to reach us. Stay curious, look up, and join us as we continue to unravel the deepest mysteries of the cosmos, one brilliant, bizarre beacon